Welcome back. In this section, we're finally going to talk about a concept known as cardiac output. And in order to do that, we need to bring some concepts together. So let's get started. First, let's define what cardiac output is. What this is the total amount of blood that is pumped out of the ventricle in 1 minute's time. So when we look at cardiac output, there's going to be two factors that directly affect it. That is the heart rate, which occurs in beats per minute, and that is the stroke volume that occurs in milliliters ejected per beat. So if we take those two numbers and multiply them together, heart rate times stroke volume, that's how we calculate cardiac output. So how do we get the numbers liters per minute from this? Well, heart rate is beats per minute and stroke volume is milliliters per beat. So if we multiply these two together, the beats cross out and you get left with milliliters per minute. Then you multiply by 1,000 and you will get liters per minute. And so instead of having a number which is going to be like 4,600 milliliters per minute, the cardiac output would be represented as 4.6 liters per minute. So it's really straightforward. So generally then, since there's only two major factors that go in, if we increase either of these two things, since we're multiplying them, increasing stroke volume or increasing heart rate will generally increase the cardiac output, but it's not absolutes. Okay, so here is a practice one where I've given you some diastolic volumes and a heart rate. So write your equations for stroke volume, for ejection fraction, and once you do that, figure out your cardiac output. All right, go ahead and stop it, do that, and I'll meet you as we continue on. All right, so now that you've worked through it, you can see how easy it is to calculate it. So let's talk about some of the things that affect it. Things affecting heart rate, autonomic nervous innervation increases. It has a positive chronotropic effect as well as some hormones. Fitness level and age could have a negative chronotropic effect. So all those affect the heart rate. Stroke volume is whether a heart is small or large can definitely change the amount of volume it can have, as well as gender, fitness levels, and preload and afterload here as well. And so just multiply those two things together and you would have cardiac output. I want to go back and look at our friend Frank Starling again. And so if we look at it, we would realize that some of these things really are not independent of each other, but actually can affect multiple places. For instance, we know that cardiac output is stroke volume times heart rate. So they both do that. But what affect heart rate also affects preload. If the heart is beating super fast, say at 180 beats per minute, there is no time for preloading, which means you're going to start at a very small preload. And even if you had a normal ejection fraction percentage coming out, the stroke volume is going to plummet. Okay. And so that would change the stroke volume in addition to the heart rate changing itself. And so not only are you changing the number for the heart rate, if it goes up or down, you're also changing you may be changing the number for the preload, for the stroke volume. In addition, myocardial contractility can affect the stroke volume. If you have an increase or a decrease in inotropic effect, how efficient that ventricle is about creating a stroke volume. So if we take all these things and we throw them back onto the Frank Starling curve, the line in the middle is the normal. And what we notice is we can shift the curve up and to the left. In other words, increasing cardiac output generally by decreasing the afterload or increasing the contractility or increasing the heart rate. And conversely, we can really flatten the curve sending it in a negative direction by increasing the afterload, thereby increasing the workload of the heart, or decreasing the contractility. Increasing the workload of the heart itself can decrease the contractility because it increases oxygen demand, or by decreasing the heart rate. So all of these things work in concert. Nothing is independent of anything else, which is why you really need to make some flow charts showing how everything interacts with everything else. And so here's an example of an overview of physiological effects. And for this one, cardiac output is at the top, so you want to start at the bottom with this lady who was exercising. And on this one, I want you to work your way through it. Realize the green arrows are things that are promoting something or increasing something. And then red arrows, which may not apply to her or may apply to her in some scenarios, are things that are going to be reducing whatever is after the arrow. So take some time and really spend some time with this slide and make sure you understand all the ins and outs of this. Now that you've understand it, let's do the easy part, which is just the math calculation. I've given you two different hearts with two different values, already pre-calculated the stroke volumes for you. I've told them they both have resting heart rates of 70. And this basically is the difference between somebody like you in class who has a normal blood pressure versus somebody that has an elevated blood pressure. So go ahead and figure out the differences in cardiac outputs. And the only thing that we've changed has to do with the person's afterload. So putting it all together, factors affecting the heart rate, autonomic innervation, and hormones can directly affect it. When we look at stroke volume, preload can be affected by venous return. Don't ask me why there's two arrows from venous return to preload, because it only needs one, as well as the amount of time for filling. The slower heart rate has more filling time. The faster heart rates have less filling time. Autonomic innervation, sympathetic effect can increase our contractility, or the lack of sympathetic effect can decrease our contractility. As well, there are hormones that can increase contractility. And lastly, the presence of vasodilation or vasoconstriction definitely affects afterload. So taking those three things, which we already learned about previously, which affects stroke volume, preload affects both end diastolic volume and end systolic volume, whereas contractility and afterload will only affect end systolic volume. And so with those, we can calculate our stroke volume, multiply it by our heart rate, and we end up with our cardiac output. So at this point, we have covered all of this. So if you've got this, pat yourself on the back, and I give you huge kudos for sticking with this and understanding these concepts. They're not super difficult, but there's a lot of tiny moving parts that need to kind of get settled in your brains. And with that, we are done with this section on cardiac output, and I will see you as we continue our exploration of cardiovascular physiology. Thanks.